Let us start our sixth lecture, and the topic of sixth lecture would be same as before, because we have already discussed that this driving force calculation would continue for next couple of lectures. Now, we were discussing these particular graph, and where we have seen that this is unstable equilibrium, this is stable, and we wanted to see what happens if we try to see the difference between G1 and G2. Let us say a particular, this ball wants to go to this particular position, then I see that G2 is lower than G1. So, there is a possibility that the ball can go from G1 to G2. Now, can it go the way this ball went to this position? Now, there is a barrier, it has to be taken to this point, and then it is to be given little push, then the ball can go spontaneously to this. Now, in this situation, though there is a spontaneity, that means though G2 minus G1 is negative, so that means there is a spontaneity, but this spontaneity is not a complete spontaneity what we had here. Rather, in order to meet the process, whether the process would take place or not, that means process means the ball goes to this point, from this point to this point. This ball has to be taken to this, that means it has to be given sufficient energy to go to this particular point. That means it has to go from G1 to G3 first, and then we can give a little push, and then from G3 to G2 it can go on its own. So, that means spontaneously it can go. So, there is a spontaneity from G1 to G2, but we need to provide sufficient excitation to that particular ball, and this excitation part is coming in the form of activation energy, and this is basically my activation energy. This is my activation energy. So, this is the energy barrier, and now though we have a spontaneity, whether the process would take place or not, that would be decided by the value of this activation energy, the amount of activation energy this ball has to acquire in order to jump over this barrier. So, if this particular barrier is smaller and smaller, let us say I started reducing this activation energy, what happens? I have a smaller and smaller barriers to cross. It is like just like a kind of hurdles. If we have a big hurdle, it is difficult to cross, rather if we have a small hurdle, it is very easy to cross. See, this easiness or toughness, that is coming from the degree of or the value of activation energy, and this activation energy would guide whether that particular spontaneous process actually takes place or not. So, if some process is spontaneous, that does not mean that the process would take place. That means a process can be spontaneous, that means there is a negative free energy change, but in order to have that particular process in practically if we have that, if we want to have that particular process, we need to cross a barrier. Okay. Now, similarly, if we try to see the ball wants to go to this point, it is not a spontaneous process, because the ball cannot go on its own from here to there, but it can go if we give sufficient excitement, it can cross this barrier and can come here. But now, let us see this and this. Can the ball go to this point on its own? It cannot. Why? Because the ball, the natural process would be the ball can roll down against the potential energy towards that potential energy lowering, rather it cannot go spontaneously up the hill, rather up the potential energy. Now, if I try to see, this is the starting point and this is the final point. Now, this is my starting point, that means G2 is my starting point and G3 is my final point. So, now if I try to find out what is the energy difference if that ball wants to go from G2 to G3, so G3 minus G2, this is a positive quantity. If the free energy change is positive, then on its own the system cannot move. So, that particular process is called non-spontaneous process. Non-spontaneous process. So, from this information it is very clear the ball can move from here to there spontaneously without giving any sort of excitement, but if this ball cannot go to this point on its own. So, if the free energy change is positive, that is a non-spontaneous process, and we can immediately say that this process is impossible on its own. But if we take this to this, then the process is possible and spontaneously possible. But if I try to see this to this, the process is possible with a bar that it has to cross this particular barrier. That means I have to give sufficient excitement. So, if some process is spontaneous, that does not mean that the process will take place. We will come to that, we will take this example while talking about the transformation of solid from liquid. Okay? Let us come back to this particular diagram. We have seen that at this point free energy change is 0, that means it is an equilibrium, and that equilibrium point is nothing but the melting point. Now, if we extend it, now this is also Tm, this is also Tm, because at the same temperature, and this is my HL, this is HS. Now, at this temperature, the difference is HL minus HS. Now, HS minus HL, in case of thermodynamic state functions, these are all thermodynamic state functions. Now, whichever I am writing, wherever I am trying to reach, let us say I am trying to reach from liquid to solid. So, then solid would be my final state. So, it should be final minus initial. In this case, I am subtracting liquid enthalpy, I am subtracting solid enthalpy from a liquid enthalpy. That means my final state is liquid. So, that case, what is this value? This value becomes positive, means this is higher than this, so this becomes positive. But if I try to subtract same thing, if I try to do HS minus HL, which becomes negative. Now, interesting, here things are becoming interesting. Now, if we get liquid out of solid, we see that it is a positive quantity, and if we get solid from a liquid, then we get negative value. Now, as per our understanding, when we have a melting, we absorb heat. Okay? So, that means solid has to absorb heat, and when system absorbs heat, that means the liquid is forming from a solid, it has to take heat. So, that whenever a system absorbs heat, we call it endothermic process. Okay. Now, in our sign convention, endothermic process, the state function change is a positive quantity. Now, you see solid going to liquid, the value becomes positive, that means the liquid solid has to absorb heat, okay? And then it can go to liquid at that particular temperature. But if I try to find whether solid forms from liquid, then it is an exothermic process, because it has to release heat. Okay? You see there is a negative quantity, it releases heat. Okay? So, again the convention is right, fine. So, that means this is my exothermic process, this is my endothermic process. And interestingly, I see that there is a huge change in enthalpy. If it is liquid to solid, I am seeing that the enthalpy reduces from this point to this point, and if I see solid to liquid, enthalpy increases from this point to this point, and that time, even though there is a lot of heat capacity change or enthalpy change, I do not see any change in temperature. And where this is possible? This is possible at melting point, and that time, that particular difference we all know, that is called latent heat of fusion or melting if solid goes to liquid. So, that means this difference is a latent heat of fusion or melting. In our sign convention, we would consider this as del H m, and here m is melting, here also T m, m is melting. So, that means that is melting enthalpy or latent heat of fusion or melting. And now, these latent heat of fusion or melting, we have to quantify what is the amount of material. We measure in the form of latent heat of melting or fusion per unit mass or per unit mole, or it can also be converted into per unit volume. And you would see that in our purpose, later on you will see initially this value is given energy joule per mole, and later on we will convert this particular unit to joule per meter cube. We can convert this in many form. So, if it is mole, we will just divide it by molar volume, that time it will become per volume. Okay. So, now we will come back to these particular term, because these particular term would be very, very crucial. Since this is a constant term for a particular metal at a constant pressure, okay, whenever the solid goes to liquid. So, these we can call it as a reference data, and these reference data will be used to find out the enthalpy change at any other temperature, Okay. How would we do it? Okay. And before going to that particular calculations, now let us see what happens if we change this particular point. If we take this, if I go, this is my temperature, if I go this way or if I go this way, what happens? Now, if I go this way, what would be the spontaneous process? And in order to find spontaneous process, I need to see which way the free energy is reduction. That means, which way the change in free energy would go to negative. Now, here if I try to see, if I see that this way the free energy goes negative, That means the change in free energy, if I try to see this is G prime and this is G double prime. So, G double prime minus G prime is equal to is a negative quantity. So, that means this is a spontaneous process. And now this G double prime is the free energy of what? It is a liquid. So, that means temperature greater than Tm, that means the melting point, I would always get liquid, because solid to liquid transformation would become spontaneous process, because the free energy change is negative. Now, if I try to go this way, then I would see that this, that means G S minus G L at this temperature, okay, this becomes negative. So, again it becomes a spontaneous process. That means, this transformation is possible. This transformation is possible wherever I see there is a decrease in free energy. But from liquid to solid, temperature less than Tm is not a spontaneous process, because that time free energy change is positive quantity. So, on its own it cannot transform. Okay. So, now we will come back to this, that would there be possibility that even if there is a delta T change, that means even if there is a delta T change, would we actually have solidification? That means, would we actually have solid formation from liquid? That particular information would be critical to analyze, but at least from this information it is very clear that this becomes my driving force, and the driving force is nothing but the change in free energy. Now, I am coming to that part, the driving force for phase transformation. Here I am seeing the solid is forming from liquid, and that driving force is nothing but the change in free energy, okay? And that change in free energy is negative quantity. Now, our main interest would be how to quantify this particular value. Okay. Let us get to the quantification of this value, and this quantification of this value would require a little bit of thermodynamic understanding. We will discuss that thermodynamic understanding in the next part. Okay. So, let us go to the thermodynamic understanding in order to quantify this value. Now, we know G equal to H minus Ts. Now, at the same time, our understanding says that absolute value of these state function would be very difficult, would not be possible to find out. So, we find out change in values, either del H, del S or del G. And at the same time, you see that we are not bothered about finding GS or GL, we are bothered about finding del G. Now, why this del G would be required? First, we should understand why it should be required, then we should crack our mind, or we should break our mind to see how we can quantify this. Now, in order to know that part, I am just going little ahead in this what Professor Sangal will be checking. You will be seeing that in most of the cases, for example, in case of steel or in case of aluminum alloys, precipitation hardening, you would be coming across a TTT diagram. Whenever we come across this TTT diagram, you will be seeing that he will show all the calculations, how to find out TTT diagram. TTT diagram we can find out experimentally, we can do raw experiments and find out what is the TTT diagram, these points over a temperature and time axis. At the same time, we can do simple calculation from simple thermodynamic data. For example, the data would be requiring which is del HM. data which will require is T, data which will require is the viscosity value. So, those are measurable quantity. Okay. So, those parameters if we use, we can get this TTD diagram. And in most of the cases, these TTD diagram experimentally found out values and theoretically found out values, they match with some little adjustment. Okay. But the nature of the graph remains like this, which is a C curve, this is a TTT diagram. And while considering this, while calculating this TTT diagram, we would be requiring information about nucleation rate, as well as growth rate. And interestingly, and these are called, you will see the notation would be U and V. U is basically the growth rate and nucleation rate is denoted by I. Now, this nucleation rate, it would have its own expression, and the nucleation rate expression is, if I try to see nucleation rate expression, I am just writing the expression is I equal to I0 exponential minus del G star plus del G D by kT. This temperature is in Kelvin scale, this K is Boltzmann constant. Boltzmann constant. If it is per atom, then K. If it is per mole, then this particular Boltzmann constant would go to universal gas constant, which is R. Now, in this we are seeing that there is a term called G star, there is a term called del G D. Now, this del G D as well as del G star are called, this is called nucleation activation energy, nucleation activation energy. And now, since I have used activation energy, it immediately tells me that it is talking about some barrier in the energy axis, energy distribution graph, as what we did in the just 10 minutes before. Okay. So, now this is also expressed in the form of, if it is simple homogeneous nucleation, that is called 3 pi square. Now, this term is interfacial energy, and this is gives free energy per unit volume. And this gives free energy per unit volume is nothing but this. So, that means in order to find out del G star, we need to find out what is the value of del G star, del G, and if it is given in mole, so we will just divide it by the molar volume of that particular substance and we get del G V. So, that means in order to find out I, we need to find out del G V, and this del G D is another activation barrier, and this activation barrier is nothing but the barrier for diffusion to take place in the material. Because whenever we try to find out some phase formation out of another phase, if it is a thermally activated process, then we need atom migration, and this atom migration does not take place just like that, it has to cross a barrier, and that barrier is nothing but del G T, okay, is a diffusional activation barrier, and this I is to be calculated. So, this I0 is another constant, and this is the temperature where I would like to find out I. Okay. I is the nucleation rate, that means the number of nuclei appearing per unit volume per unit time. Okay. So, that is basically decided by del G star as well as del G T. We have ways to find out del G T, but when we try to find out del G star, we need to know what is del G V. That means, I need to find out the driving force for the transformation, which is negative. And these particular term, which is interfacial free energy, okay, or interfacial energy, this is another important term. We will try to see what it exactly means. We will try to see. But why I am telling that this particular term is to be quantified, because this is needed in order to find out I. Similarly, if I try to find out growth rate, the expression is u proportional to 1 minus exponential minus delta G m. I would say m means, or let me put only gel G in the molar quantity RT. So, this is the term. So, here this term is also this term. So, we need to find out this term also. Now, we are wondering that we said that this, for finding this TTD diagram, we need to know nucleation rate, we need to know growth rate, and overall this particular graph says the overall transformation kinetics, and this overall transformation kinetics is given in the form of Johnson, Mel, Avrami, Kolmogorov, which is properly known as JMAK equation, which is given in the form of x, which is the fraction transform. That means, the product phase, when it is appearing in the parent phase, the fraction of that particular product phase is given by x equal to 1 minus exponential minus pi by 3 I uq t to the power 4. So, this is the expression. So, where I need, and this particular graph is plotted with some x value, and then where I need to know what is my I, what is my u, and this time is basically this time axis, and this is at some particular temperature T. So, now if I try to find out at this temperature, this point, when this point would appear, that would be decided by u and I. So, this is overall kinetics. That means, in order to find this, we need to know I, we need to know u, and in order to know I and u, we need to know del G. So, that is the reason why we should try to see first how we quantify del G. This is extremely important, because otherwise we will not be able to calculate this graph. Okay. So, now let us come to finding this value. Okay. Since we have understood what is the importance of finding this particular parameter, which is the free energy difference, or which is the driving force for that transformation. Let us stop here. We will take it up in our next lecture. Thank you very much.